So in this video, I will walk you through the Hackthon notebook where we build a stroke classifier. I will focus on two main questions: what we did to improve the performance of our classifier and how we assessed and improved its fit. So first, we loaded the training and test data sets and then performed some initial exploratory analysis. So we checked for missing values and duplicate interests, ensuring data integrity. We converted categorical features like gender, work type, residence type, and smoking status into dummy variables using one-hot encoding. We also bind continuous features such as age into age group and BMI into BMI category to capture nonlinear effects. Additionally, we applied a log transformation to average glucose level to reduce skewness. These pre-processing steps from the factual foundation of our work, ensuring that our model receives clean, well-structured input data. So next, we enhance the data set by engineering new features. We created interaction features such as BMI and age, glucose and age to capture potential multiplicative effects that are common in health risk factors. So we also combine hypertension and heart disease into a single interaction feature, hypertension heart, which reflects compounded risk. By adding these features, we moved from merely recalling definitions to applying and even creating new insights. So since stroke events are rare, class imbalance was a major concern. Initially, we used SMOTE to oversample the minority class. However, we later experimented with an alternative class weighting using light GBM skew pulse weight parameter. We commented out these SMOTE code and reassigned the original training data to our working variables. This change reduces the risk of overcompensation because the model now only adjusts for imbalance by increasing the penalty for misclassifying the minority class. Here, we not only recalling the techniques, but also evaluating and analyzing which method leads to better performance. We then split the data into training and validation sets using stratified sampling. We built several models: random forest, XGBoost, light GBM, and logistic regression, and compare their F1 scores. So for our best performing model, light GBM, we set up a Gray Search CV to tune hyperparameters such as an estimator, learning rate, max steps, number lifts, and crucially, skew pulse weight. During hyperparameter tuning, we ensure that we aren't relying on synthetic data from SMOTE, so we trained on the original dataset with class weighting. After selecting the best model, we further refine performance by tuning the decision threshold on validation set, iterating over a range of thresholds to maximize the F1 score. In the procedure terms, we followed a systematic approach, generating candidate models, evaluating them with cross-validation, and then tuning the threshold. This step-by-step method not only demonstrates our procedure knowledge, but also shows the understanding of the cause and effect relationship in the model training. So after tuning our model, our next step was to thoroughly evaluate its performance to ensure it fits the data well and would generalize to unseen cases. So we began by generating detailed classification reports that broke down precision recall and F1 scores for each class, giving us a clear picture of where the model was performing well and where it might be struggling. We also use confusion matrix to visualize the true positives false positives, true negatives, and false negatives, which helped us understand the trade-offs of our model was making. In addition to the standard matrix, we plotted the ROC and precision recall curves. These curves were particularly useful for assessing performance across different thresholds. By carefully analyzing these plots, we were able to fine-tune the decision threshold to maximize the F1 score, ensuring a balanced trade-off between precision and recall in the context of our imbalanced datasets. So moreover, we performed cross-validation to get stable performance and estimates across different splits of the data. Although we didn't explicitly plot learning curves, we closely monitored the gap between training and validation performance during cross-validation. The small difference between these errors reassured us that our model wasn't overfitting or underfitting. Overall, this comprehensive evaluation gave us confidence that our best performing light GBM model was robust and well fitted, setting a solid foundation for making reliable predictions on new data. So, to summarize, we improved our classifier's performance by refining feature engineering, handling class imbalance with class weighting instead of SMOTE, and thoroughly tuning hyperparameters and thresholds. We assessed the model fit by comparing training and validation performance using cross-validation and multiple evaluation matrix, ensuring that we recognize the fundamentals of model evaluation while also effectively in balancing precision and recall. This comprehensive approach helped us achieve a robust and well-fitted model. Thank you for watching.